Singer Eternal Voice. So our topic for today is chemical equilibrium partial pressure expression. Chemical equilibrium, chemical equilibrium, nabubulol. Okay, chemical equilibrium expression of the partial pressure is just like the same mode with equilibrium constant of the concentration expression. Okay, so it's basically the same. We follow the same pattern. Okay, so we have now problem. Problem number one: a mixture of sulfur dioxide and oxygen gas were maintained at 800 Kelvin until the system reached equilibrium. The equilibrium mixture are sulfur trioxide is equals to 5 times 10 to the negative 2 molarity moles per liter. Okay, sulfur dioxide is 3 times 10 to the negative 3 moles per liter, and oxygen gas is 3 times 10 to the negative 3 molarity. Calculate the chemical equilibrium, okay, of partial pressure of the expression. Okay, equilibrium constant of partial pressure expression is Kp. Now we cannot compute Kp if we will not compute first the chemical equilibrium expression of the concentration. Okay, but sometimes, guys, the problem will be modified into a direct way of solving the equilibrium constant of the partial pressure expression, in which the data are expressed in partial pressure itself. But here, this is expressed in molarity. Okay, it is also logical because we have a specific formula to follow, something like that. So this is not dimensional analysis or conversion way of solving the problem. So this is really based in the standard formulas to be used in chemical equilibrium formulas. Okay, so if you will remember that the rate of the forward reaction is equal to the rate of the reverse reaction, then we can have the ratio and proportion for that. If it is in equilibrium, then we need to take out the similarities quantities, and after that we can come up to the chemical equilibrium constant. Okay, so I discussed that last 3 days ago, and we don't want to go back that again, the derivation why it come up to have like this formula. Okay, now so it's very clear here that we need to memorize, because we can also compute this through derivation, but it will take a longer time. But it's better to memorize because it's very easy also to memorize only 3 quantities, or let us say, yes, 4 quantities involved in one linear equation. Okay, this is gonna be Kp is equal to Kc times universal gas constant times the capital T raised to the power change in delta N. Change in delta N meaning the change in the number of moles, meaning say the number of moles in the products total. For example, if you have 2 or more products, and then minus to the number of moles in the reactants also. And you have to add both the number of moles in the products minus the moles of the products and reactants, and that will be your delta N. Okay, so sometimes it could be also negative. Okay, due to there are a lot of number of moles in the products than in the reactant, something like that. Or we can say that in another way around. We can say the total number of coefficients of the products minus the total number of coefficients in the reactants should also equal to the change in the number of moles or change in the coefficient. So here we treat directly that the number of coefficients are equal to the number of moles. Okay, something like that. Okay, in which we regarded that over and over again as that in our theory, right? Something like that. So this is our equation to be used. Okay, so this is standard. Always take note this kind of formula because always it will come out also in the future examination. So normally in the board examination, if you're taking up BS chemistry or BS chemical engineering or any science related course, especially tackling the subject of general chemistry lecture, okay, in this topic, chemical equilibrium of the partial pressure and also the chemical equilibrium constant of the concentration. Okay, now we need to have a solution proper. We'll start solving this particular problem. Okay, solution. Okay, but before that, step one, data are given. Okay, the given are this. I have to underline. Okay, the sulfur dioxide, the oxygen gas, okay, the SO3 in terms of the molarity. Now we need to solve Kc first because the data are expressed in concentrations. So if that is expressed in partial pressure, then it's also very easy to do that. Okay, no need to use this. We will just use the Kp is equals the partial pressure of the products, okay, raised to the number of moles over the partial pressure of the reactants raised to the power the number of moles. But in here, these are all concentrations. That's why we need to use this formula. Okay, like that. So if we have a reaction, chemical reaction, so this is still again classification of matter under our flow chart in studying general chemistry. So this is classification of matter composed of the pure substance and the mixture. So this is particularly a mixture, and this is this is a heterogeneous mixture because oxygen gas, okay, and then no, it's not. This is homogeneous because these are all gases. Homogeneous mixture. Okay, so like that, all gases, right? So this is homogeneous mixture. So we need to keep track also to the flowchart so that we can understand what particular topics we are in or what we have done, something like that. Okay, now we have the chemical reaction of SO2, okay, is equal to, okay, SO2, sulfur dioxide, this is gas, right? Okay, like that subscript and then open, close and open parenthesis or parenthesis, the state or the phase of matter. So this is small letter G, gas, okay, plus oxygen, okay, and also gas is equals to like this, okay, is equal to SO3, okay, diba? So the oxygen, the number of protons of oxygen will be donated to the another oxygen. Okay, so that's why it will become SO3. So this is basically synthesis reaction or combination reaction, the type 1 chemical reaction in chemistry. So combination only. So it is just very basic to consider, right? Because combination. Okay, so this is SO3. Got the point? Like that. You got the point. So it's gonna be like that, SO3, okay, gas, still gas, okay, like that. So what we don't consider is O4 for this because it's very, very difficult to balance if we will start with SO4. You get the point? Something like that. And normally, oxygen gas will only donate 1 proton, not 2 proton. You get the point? Okay, something like that. So it's stable starting with SO3. Get the point in this case. Because actually you can see also SO2 plus O2 is equal to SO4 and it will be balanced immediately without question. But why we'll never choose the product? We use SO3 instead of SO4. Something like that, right? Okay. Get the point? SO4 is sulfate. Okay? Like that. Say for example is SO4, okay, SO4, okay, gas. No, it's not gas, it is solid. Okay, so there are two reasons. Aside from that is not stable, it's also solid in nature, and we cannot produce solid by adding gas plus gas. Okay, and here, this is O3 is really existing as a gas. That's a secondary reason. Okay, but the first reason is due to the, stability of the product. Okay, so it's gonna be SO3. See, if you use SO4, it will balance immediately the oxygen and sulfur. but it is solid. It will become a magic. If you add two gases, it will produce sulfate. You get the point? It will become a salt. Okay, so we have sulfur trioxide. Okay, here, this is the equation. And we need to balance this, okay? So this is using trial and error method because we need to balance first the equation. In all chemical equilibrium computation or problem solving, it's very, very important to balance first the chemical reaction before proceeding. That's the requirement, right? Okay, so let's balance the equation. Trial and error. We do this. Oxygen 4 in the reactant, and this only 3 here. Now, we cannot put 1 because it will become an odd number. 3 times 1, 3. So it will never compensate here. So we need to put 2, okay, in the SO3. Because I put 2 in the SO3 because the oxygen in the product is deficient. We always put in the deficient side. Okay, so 2. Okay, so it will be adjusted to the reactant. And now we balance this. It's going to be 2S and then S also, 2 also here. So sulfur 2, oxygen 4, oxygen 2, then 6 and 6 in the product. So perfectly balanced by visual inspection and a little bit of trial and error method. It's going to be the balanced chemical equation. Okay, guys? And then we need to compute now for the Kc. Okay, Kc, or the equilibrium constant expression of the concentration, is equal to the concentration of the product SO3 raised to the power 2. Okay, because this is the number of moles or the coefficient over, okay, SO2 raised to the power 2. Okay, like that. And oxygen gas raised to the power 1 or nothing. It's just the same. I remove the gas because all are gases. Okay, to save also the ink and to save also, you know, a lot of effort in doing that, in writing, right? Okay, so it's gonna be like this. Substitute the value of its O3 concentration. This bracket vertical, you know, position like that, not the curve, is a representation of concentration. When you put the bracket, that means concentration. Okay, or actually it's just the same if no bracket, but to make it understandable. Okay, because the unit will always matter. Okay, if there's no unit, then understood to be concentration. You get the point? Okay, so it's gonna be like a capital N. Okay, but to remove the capital N, that's why I put the bracket, and this is concentration. Okay, now, SO3 concentration, mga palangga, 5 times 10 to the negative 2. So I need to avoid the exponential, so move to the left, because it's negative exponent in math, algebra. You need to move to the left, because it's negative. So 1, 2, ganun. So 1, 2. This is 0.05. 1, 2, okay? And then we set the power 2, okay? Like that. For SO3, okay? SO2 is 3 times raised to the power negative 3, so move 3 zeros to the left. Okay, like this. Okay, 3 zeros to the left. 1, 2, 3. So that it's 0.003 raised to the power 2 here in the formula, right? And then the other one is oxygen gas is 3.0 times 10 to the negative 3 molarity. So it's just the same, right? Okay, I need to say 0.003, okay, without exponent because it's only 1 in the number of moles in the chemical reaction. So, calculator please, you have the Kc here. Okay, guys? And then, actually, this is very easy, right? Because it's direct substitution, but you have to understand the concept. Okay? Something like that. Okay. Calculator, please. Okay, 0.0003. Okay. Equals 2 times 0.003 is equals to 2.7 times the negative 3, the denominator. Okay. Like that. Get the point. 2.7 times 10 to the negative, okay, negative 8. And then the numerator is 0.05 raised to the power 2. okay, 0.05 raised to the power 2 is equals to 2.5 times 10 to the negative 3, okay? Okay, meaning to say 2.5 times 10 to the negative 3 divided by 2.7 times 10 to the negative 8. So by visual inspection in math, again algebra, if you try to divide, you need to add the two exponent, okay? Because this denominator will go up, so it will change the sign. For example, if it is negative 8, it will become 10 raised to the power positive 5. Okay, then 2.5 divided by 2.7 times 10 to negative 3 plus 5, negative 3 plus 8. Okay, the negative 8 will become positive 8. Okay, so negative 3 plus positive 8 is equals to 10 to the 5, the exponent, times 10 to the 5 the exponent. So 2.5, 2.7 to simplify so that I will never use exponent in the calculator. Okay, like it's 2.5 divided by 2.7 is equal to 0.93. Okay, so 0.93, so it's become 1. So this is negative, right? So 9.25 negative 1. Exponent, so negative 1 plus 5, this will become 4. So 10 to the 4. And then it's going to be 9.2 or 9.3. Okay, 9.3 times 10 to the 4. Okay, get the point? Because I have 0.93 when you divide it by 2.5 to 2.7. So 0.93, okay, we need to move that to the left, to the right again. So that's negative 1. You get the point because it's going there, right? So 1, that's positive 1, sorry, to the right positive 1, and then plus 5, and it will become 4. Okay, 9.3 times 10 to the 4. Or to make it sure, just carry the exponent, okay, in order you will check that it's correct or not. Something like that, because it's better to make sure, right? Okay, it's equals to exponent to the negative 8 is equals to 1, 2, 3, 4. So 9.2592 raised to the power, okay, positive 4. See? It's correct, positive 4. Okay, or 92,592 if you want to make that in figure without any exponent. Okay, so our KZ now, okay, erase this one. So we have now our KZ. I have to erase everything because I have a very, very small dimensional whiteboard. The length and the width are very, very small. You get the point. The surface area of my whiteboard. So I can accommodate all my, expansion of my writings. Something like that. Okay, so KC is equal to 9.3 times 10 to the 4, mga kalangga. Okay, ganon. So I have to erase this chemical reaction. Okay. Okay, or we will remove this entire problem, right? Because we already discussed to you and you hear that already. But this is gonna be the specific problem we have now. Okay, mga kalangga. And then there's gonna be the specific formula to be used. Kp is equals to Kc times the universal gas constant, then the capital T bracket raised to the power delta N. So we will just imagine, because I already erased the the chemical equation due to the space very limited. So we just memorize that it has so it has a 2, right? 2 moles. So we compute first the delta N. So the moles of the product is the SO3. It has 2 moles, okay. 2 moles, ganon, okay. Minus the moles of the product, we have the SO2 and O2. So, okay, 2 ang SO2 and then 1 for oxygen gas. So 2 moles plus 1 mole of oxygen gas is equal to 3. So 2 minus 3. So our delta N will be negative 1. Okay. Our Kc to be used here, let's be clear enough that we have 2 values of the universal gas constant, or the gas constant that we will keep on memorizing that for a long time ago, right? Okay, like for example, okay, Okay, capital R, for me in my case, I've memorized only two when I was in first year college until fifth year college and up to now. Okay, so we have 8.3145 times 10, okay, joules, okay, mole, Kelvin. And we have also another one. We have 0.08206, okay, liter atmosphere, mole, Kelvin. So you will remember, guys, that the numerator of this particular unit of measure or measurement is in terms of the word. Okay, here. Okay, so here, because this is the unit of energy, joules is a unit of energy, and liter atoms is a unit of energy also. You get a point? Because that is volume is a liter and pressure is ATM. So a liter atmosphere. So work is equal to pressure times volume. That's why it's gonna be the numerator, and this has been taken in the thermodynamics properties. Okay, that's why we have the formula PV in RT. So actually, the PV there coming from the thermodynamics. Okay, W is equals to P times B, or work is equals to the pressure times the volume, something like that. Or the change in volume times the pressure. But normally, in in basic problems, normally there's no change in volume. Okay, so what they mean there, delta V, final change of volume, but we normally treat that as V lang siya talaga if there's no changes. That's why pressure times volume. Okay, this I teach you because sometimes you forgot the numerator. So don't forget that it's the unit of work. Okay? Okay, that's why I emphasized. Okay, now in here, so you check the compatibility of the units of the measurement so that you can cancel out and simplify your correct equilibrium constant of the pressure of the expression. Ganon. So substitute the Kc. Kc has no unit because it's equilibrium constant. Okay, very obvious, right? So unitless. So 9.3 times 10 to the positive 4 times the universal gas constant. And now we will be able to use the 0.08206. Okay, something like that. This one. Okay, 0.08206 liter atmosphere, okay, mole, Kelvin. Why we will use this? Okay, why we will use this, mga palangga? Because our unit of the molarity, capital M, is moles per liter. And it's easy to cancel here. Okay, something like that. But in the other one, there's no liter at the numerator. How can we cancel the joule? That's why we don't use the 8.3145 joules. But in physics, we'll normally use that. Because, in physics, branch of science that deals with the study of matter and energy. So always dealing with energies. Okay, that's why it's very easy to use this first value of universal gas constant. But in here, we need to use this universal gas constant 0.08206 liter atmosphere, mole, Kelvin, something like that. And then we need to plug in the values. Okay, and in the Kelvin, here, capital T is always a Kelvin. Okay, because if you're using Celsius, Fahrenheit, and the other one is Rankine or Rankine, then it will never cancel in the unit of the universal gas constant. So you need to be extra careful with the units of measurement compatibility issues. Okay, like that. Our temperature here is being mentioned, okay, 800 Kelvin based on my memorization. Though I erased the problem, it's still registered in my brain cells. 800 Kelvin. Okay, like that. Okay, see, we can cancel the Kelvin. Okay, like that. You get the point. And then we have the delta N, which is -1. So -1. Okay, so this whole thing, first RT, whole thing, meaning we need to multiply first this. This is following the algebra math rule. That is PM dash or PM dash. Okay, that means first you need to calculate what's inside in the parentheses, and the second will be the multiplication, third will be the division, fourth will be the addition, last will be the subtraction. That is really the rule. PM dash or PEM dash. You get the point. Why I said PEMDAS? Because sometimes there's an exponent. But usually there's no exponent, so PM dash lang siya. Okay, but sometimes have, that's why PEMDAS, PEMDAS, and sometimes also PM dash lang siya, no E. The acronyms I used. Okay, repeat, algebra rule, PEMDAS. Okay, parentheses, exponent, multiplication, division, addition, subtraction. These are the operations that you will be used systematically. Okay, if you rumble that one, your answer will be wrong in algebra. Okay, or in a basic math. You should start with the parentheses, exponent, multiplication, division, addition, subtraction. Okay, now there are situations that there's no exponent involved, especially in linear algebraic expression. So we can say PM dash lang siya without capital E in the acronym. So, okay, parentheses, multiplication, division, addition, subtraction. So that's rule. Okay, just like politics and law. Okay, country laws. So we have rule to follow, something like that, rule to follow. Okay, now let's calculate that one. Now guys, if we have an exponent of -1, so we can directly put that in the denominator. But for me, I don't want to do that. Okay, okay, to make it simpler. Okay, so let's do this. Okay, so 8.08206, okay, 0.08206, okay, times 800 chupa chuchu is equals to 9.3 times 10 to the 4, okay, 65,648, okay, and -1. Now, okay, now, this -1 is only for the parentheses, not for this. Because I know your parentheses should be done first in the algebra. You get the point? If you times this in the other side, then you will become wrong. Okay, so it's gonna be 9.3 times 10 to the 4, or you will see in that way, it will go down. Okay, this is 1 over 65.648 in math, right? If, for example, if I have 10 to the -1 in math, you will say 110 raised to the power 1. It's just the same here. Okay, so I put 65.648 raised to the power 1. Since anything raised to the power 1 is just simply nothing. So that's why it's gonna be like this. Okay, then multiply. Because the third is multiply, see? And because we have exponent, that's rule. So multiply. We follow the rule in algebra. Okay? So that if you never follow that one, then you'll be wrong. Okay? Something like that. So actually it's very, very basic, but we need to remember that all that time. Huh? Okay. So 9.3 exponent to 4 divided by 65.648 is gonna be 1416.64. It's gonna be move the zeros to the left. So 1, 2, 3. So it's gonna be 1.42 times 10 to the 3. This is your KP already. Okay, to make sure, use the scientific calculator just to prove that it's correct. Okay, so there's something like that. So 1, 2, 3, so it's correct. Exponent 3 really, because this is a positive value. Okay, your equilibrium constant partial pressure of the expression will be equal to 1.42 times 10 to the 3. Now, this is the most important thing. Okay, now we need to correlate with the theory. So something like that. Because, in the future examination, it's not enough to get the answer. We need to prove and validate our answer based on principle and concept and theory. Okay, it's not enough. Okay, like that, because sometimes the choices are very near. Okay, or you don't know, right? So, KP is equal to 1.42 times 10 to the 3. You know the value. And I have also the formula. KP is equal to Kc times the gas constant times T to the power, the change in the number of moles. Now, if you try to compute for Kz also will be equal to Kp over RT raised to the power delta n. So the relationship of Kc and Kp is directly proportional with each other. As the equilibrium constant of the concentration will increase, also the partial pressure equilibrium constant will also increase, something like that. For example, in this case, you're asked to compute for the Kz. It's also increasing. It's directly proportional with each other. Now, if your Kz will be going low, small, and your Kp is high, that means your answer is wrong. So, meaning to say that's not valid already. So that's the purpose of taking the relationship through that formula and equation. And aside from that also, we need to remember also another theory for this. Since Kp and Kz are directly proportional with each other, okay, it's gonna be like that, guys. If you know the basics, it's very good to have a little bit of confidence to pass certain examinations. Okay, like this. So we have Kp is directly proportional to Kz, something like that. Since we know the theory of chemical equilibrium also, that if Kz is greater than 1, like that, so if Kc is greater than 1, so what will be happening to chemical equilibrium? So this point in time, we will now apply the Lee-Chatelier's principle in 1901. In 19th century, Mr. Lee-Chatelier discovered the chemical equilibrium. Okay, in terms of this 4 or 5 stresses. The stresses are pressure, concentration, volume, number of moles, something like that. Okay, then if more of these moles, what will be happening? It will be shift to the right, shift to the left. If I will put more number of moles in the reactant, what will happen? It will shift to the right or shift to the left, something like that. But in this manner, we have to account the concentrations. Okay, the equilibrium concentration constant is also directly proportional to the concentration. Okay, so KEQ general equilibrium constant is directly proportional to the concentration. Okay, meaning concentration, it could either be the concentration of the reactant or the concentration of the product. It doesn't matter at all because this is general. Okay, not hypothesis, this is already a confirmed principle. Okay, like that. So, okay, now if Kc is greater than 1, so if you have a reaction of sulfur dioxide plus oxygen gas is equals to sulfur trioxide, now the equilibrium will shift to the product. Meaning to say, more of the products will be produced, the concentration of the products will increase. Get the point? Now, in certain examination, always like that, what will be happening if your equilibrium constant of the concentration will increase? It will shift to the left, it will shift to the right, remains the same, not affected. E, all of the above, like that, none of the above. Then if you don't know really the basic foundation of the relationship, then you will be lost, even though you know how to solve it. You get the point? So that's the problem of sometimes you need to adopt the theory, and not sometimes, all the time. Okay, because if you're loving and solving and you don't know what you are final destination, what is your purpose? Why you solve that problem? That's theory. Okay, solving the problem is an application or tool to understand really what is the theory. Okay, so that's only the tool, but that is not really the direct learning you want to. You get the point? Okay, so that you can understand the principle. Then we need to back up with measurable data through solution of the particular data. That's why you need to compute. Okay, that's only an additional to prove your theory. You get the point? That's scientific law. Scientific law are scientific equations, formulas like that. Okay, so this is the elements of scientific research. Okay, something like that. So, if Kc is less than 1, okay, then your concentrations of the reactants will be higher and the equilibrium will shift to the right. So, in this correlation, then I can say that the Lee-Chatelier principle in 1901 states that, listen very, very carefully, okay, whenever a stress is applied to a system of equilibrium, the equilibrium will shift to the direction so as to reduce the stress. Something like that. So we think of like a seesaw, a balanced seesaw left to the right. What will happen? For example, if there's a child in the seesaw like this, like again in the playground, children's playground, something like that. What will happen if there are two kids on the other point and there are also one kid in the other part? Then what will happen? It will go down because the weight of of the two are greater than the other one. It's gonna be like that also in the chemical reaction, okay, or in the chemical equilibrium. Okay, you get the point. So it's gonna be like that. So any questions so far for this topic, and then I'll be able to show you another problems related to chemical equilibrium also. Okay, guys. Okay, thank you so much for listening for this specific vlog regarding chemical equilibrium. Partial pressure equilibrium constant expression. Like that. Okay, I'll be showing you another example later on. So if you are not subscribing yet my channel, you can subscribe, guys. And you can comment down below in the comment section also and click the notification bell for some newest updates of the singer. I don't have microphone today because my microphone is damaged. My gosh, okay? Like that. Thank you so much. Bye bye, God bless everybody. See you later.